Okay, hello. So, once again, the mysterious voice in the ether welcomes you to an AS Physics paper. So, let's get started. Yeah, 7 questions should be good. So, use the definition of power. So, definition of power that they are looking for is power is work done per second. That is an important thing to remember. So we often talk about the idea of power being energy used per second or something like that, energy per second. The specific definition is work done per second. Let's write that down. Now, work has the same units of energy, and therefore from that you can get the units that they're after. So I think that one's the main point to remember is this idea and the fact that it's work. Okay, use an expression for electrical power. So that's going to be P equals IV. Or, yeah, that one works. To determine the SI base units of potential difference. So V equals P over I. Well, we just found the SI units of power. Current is a nice and simple one because that is an SI base unit. That's just amps. And so that one's nice and easy. Okay, question 2. Define speed and velocity. So this is just your standard definition of a vector, right? So speed, you know what speed is. The key point about this question is what do we mean when we talk about a vector, i.e. velocity, as opposed to a scalar like speed? That's just a standard one that you need to learn. It's a very common question for them to ask. Okay, we have a bouncing ball. Excellent. Its velocity looks like this. Marvelous. Air resistance is negligible. Without calculation, use figure 2.2 to describe the variation with time t of the velocity of the ball. Okay, so to 2.1 seconds. So 2.1 seconds is here. So this is the ball falling, it bounces, and then it gradually decreases to rest. So at this point, it's actually at rest. So it's back at its maximum point again. And then in this direction, it's falling back down. So yeah, the first one, it's falling down. So you've got 1, 2, and then this part is 3. And this is 1, 2, and 3. So that's the only kind of niche to that. Niche? The words. Nuance to that is the fact that this part is where it's rebounding up, and so this point it's not moving because the velocity is 0. Don't get it confused with a displacement time graph. Okay, calculate the acceleration of the ball after it rebounds from the ground. So, acceleration is the gradient of a velocity time graph. This is where it's rebounding, this very steep reversal of the velocity, and so you're looking for its velocity after it rebounds, or rather its acceleration, and its acceleration is just the gradient. So, draw a triangle, preferably a really big one, and yeah, says show you're working. That means that you actually need to draw the triangle on the graph. That's important. That's what they mean. That's what they're after. Calculate the distance moved. So the distance moved is the area under a velocity time graph. Now, distance is a scalar. So the distance moved is going to be this area plus this area. Okay? However, the displacement is going to be, let's call these A and B, right? This area is you've got a negative velocity here, right? So this is where the ball is bouncing back up. it's going in the opposite direction. And so when you go for the displacement, which is where direction matters, you're going to have this area minus this area. That's the key difference between these two. So this is the total area. This is the area in one direction minus the area in the other direction. So it tells you, yeah, the displacement. All right. Sketch the variation with t of the speed of the ball. So speed is just the magnitude of the velocity, right? And so all that means is that when the velocity is negative, you still have a positive speed, because speed is always positive. And so you're just going to essentially flip this section of the graph up so that it would be a spike in the upwards direction rather than the downwards direction. That's all you're looking for there. Okay, we have two balls supported by long strings. We have masses, velocities, and we have a collision. So the positive direction is horizontal and to the right. So they've defined positive being this way. So that means that x has a positive velocity here and y has a negative velocity. Use conservation of linear momentum to determine the mass m of y. So what that means is that the momentum before the collision, the total momentum, which you can work out from here, must be equal to the total momentum after the collision. And obviously both of those total momenta are going to depend on m. So you're going to have 4.5 times 50 minus 2.8 times m, and then similar for the second set after the collision. They have to equal each other. You can find m from that. Whether the collision is elastic. So the definition of elastic is kinetic energy, total kinetic energy conserved? This collision is not elastic, I think, unless I am much mistaken. Yeah, so the magnitude of both of our velocities has gone down significantly. So we've lost quite a lot of kinetic energy here, actually. So our collision is not elastic. The key idea here is we have lost kinetic energy, so it's not elastic. Use Newton's second and third laws to explain why the magnitude of the change in momentum of each ball is the same. So this is the idea that for every action there is an equal and opposite reaction, right? And what that means is that if x is exerting some force F on y, then y must be exerting the same force F on x, because the contact forces are equal and opposite. And then Newton's second law, so that was the third law. Newton's second law is that force is the rate of change of momentum. So if you have the same force on each ball for the same amount of time, because they're in contact for a certain amount of time, then you're going to have the same change in momentum overall. Okay, question 4. We have a spring and it looks like we're going to crash a cart into it. Seems like fun. So this is a compression graph, force extension essentially, for our spring. Use figure 4.2 to show that the compression of the spring obeys Hooke's law. Okay, fair enough. So Hooke's law, F equals kx. Yep. So what we want to do is A, show that it has a constant gradient. B, we want to show that it's going to go through the origin, right? So the origin, the 0, 0, isn't on this graph. We've plotted our axes starting from 0.5, 1.5, as we can if we so desire. What we want to show is that we can find the gradient of this graph, and then we can take any one point. This one's got nice numbers on, so might as well pick that one, and show that if we map our graph back, that when we reach 0, 0, we will reach 0, 0. So that's the idea here. And it has a constant gradient. And so that gradient you can find, that will be K. Determine the spring constant. Okay. So, determine the spring constant, that's just the gradient of your graph. It may be that for this question or thereafter is that you say that it's a straight line, but I think the key idea here is to show that it goes through the origin. Determine the spring constant, that's just finding the gradient that you already said was K. Determine the elastic potential stored in the spring due to the cart being brought to rest. So, the cart comes to rest when F is 4.5 newtons. So that's up here. Now, there are initially our spring presumably is at its natural length, so it has no compression on it. Unless it says otherwise. It doesn't. Excellent. So, elastic potential energy stored is the area under a force extension graph. But that is kind of hard to do here because we don't have the whole of the graph, right? So there are two ways that you can do this. Either you can recognize that this is in fact a triangle, and so your area is going to be a half times width times height, right? Height is 4.5, the width is 1.8, yeah, 1.8. So a half times 4.5 times 1.8, convert this into meters because it's in centimeters. So that's one way of doing it. The other is to use the formula that the energy stored in a spring is a half k x squared. Either of those will work here. Probably what they are after is the area and recognizing that it's a triangle so that you don't need to see the whole area of the graph. You can just do a half times base times height. Okay. Calculate the speed v of the cart as it makes contact with the slider. So, when we have compressed and the cart has come to rest, we have turned all of our kinetic energy into elastic potential energy. Therefore, it must have started out with this amount of kinetic energy. Kinetic energy is a half m v squared, and from that you can get v because you already know m. Okay, we have variation with potential difference v of current I for a semiconductor diode. Fair enough. Use figure 5.1 to describe the variation of the resistance of the diode between v equals minus 0.5 and v equals 0.8. Okay, so minus 0.5 is over here, and 0.8 is just where the graph stops, i.e. by here. Right, so that just means the whole of the graph. So, what is going on over here? Well, at this point, we've essentially got infinite resistance, right? Because we are not allowing a current to flow. If we're not allowing a current to flow, we've essentially got infinite resistance. And then the resistance decreases rapidly after that. Okay? The more current flowing for a given voltage, the lower your resistance. That's the key idea here. So at these low voltages, when you've got no current flowing, your resistance is stopping any current flowing. It's essentially infinite. And then after this, it rapidly increases. It rapidly decreases. So yeah. All right, that'll do. On figure 5.2, sketch the variation with potential difference of current I for a filament lamp. So this is just a picture that you need to learn. The description is in the mark scheme. It's not worth saying much more about that. Filament lamp, diode, which obviously looks like this, and then a kind of generic ohmic conductor, a wire, for instance, which is just a straight line through the origin, and this one is just a not very straight line. So yeah, those are the three that you need to remember. Okay, figure 5.3 shows a power supply of electromotive force 12 volts and internal resistance half an ohm. We have a filament lamp, power of 36 watts when the potential difference across it is 12 volts. Calculate the resistance of the lamp when the potential difference across it is 12 volts. So this is P equals V squared over R. Right, this is one of your standard ones. You've got P equals IV, P equals I squared R, P equals V squared over R. They're all just kind of variations on one another, and V equals IR. Right, P equals IV, V equals IR, everything else just comes from those. Here is your idea. If you're given 12 volts and you're given a power, you can calculate a resistance. The switch is closed and the current in the amp is 2.8 amps. Current in the lamp is 2.8 amps. Calculate the resistance of the lamp. So we have a current I in our circuit. We have 12 volts overall. Our total resistance is our resistance of our lamp plus half an ohm. So we know that our current, we have V equals I R, or I equals V total over R total for the whole of the circuit, because we're just in series here. And so our resistance is going to be, so we've been given a current, we've got a voltage, our total resistance is the resistance of our lamp plus half an ohm. So we can calculate the total resistance and then take half an ohm off of it. Explain how the two values of resistance calculated in C provide evidence for the shape of the sketch. So at that point, you're just saying, well, okay, my potential difference has changed, and so has my resistance. Okay, state what is meant by diffraction and by interference. These are just definitions that you need to know. Light from a source, S1, is incident on a diffraction grating. So, diffraction grating equation, as standard, n lambda equals d sine theta. Calculate the number of orders of diffracted light. So, when you are projecting onto a screen, sine theta cannot be great. Theta cannot get bigger than 90 degrees, right? That makes sense. If theta was bigger than 90 degrees, we'd be projecting backwards at that point, and we have a screen over here. If we're projecting light backwards, it's never going to reach the screen. If the screen is infinitely long, then we can get essentially approximately close to 90 degrees if we go really far out. What this means ultimately is that sine theta cannot be, I mean, in general, but for this, sine theta goes from 0 to 1, right? 0 at theta equals 0, 1 at theta equals 90. We have lambda and d, and so what we're looking for is the maximum possible value of n. So n equals d sine theta over lambda. That came out horribly, but never mind. Maximum value of sine theta is 1, so n max is equal to d sine theta max, which is just d over lambda. This will come out to be a decimal number. N is a whole number, so you round it down to the largest whole number that fits in, right? Because if you round it up, then you're going to be outside the screen. So you round it down to the nearest whole number. You truncate it. A second source is used in place of S1. the light has a single frequency lower than that of the light from S1. State and explain whether more orders are seen. So, C equals F lambda for light. Okay? So, that tells us that lambda equals C over F. The larger our frequency, the smaller our wavelength. Or, in this case, if we have a lower frequency, we will have a larger wavelength. If our wavelength is larger, our n max is going to get smaller. So we will not see more orders, we will see less. Okay, I believe this is the last question. What is meant by an electric field? That's a definition. Force per unit test charge, positive charge. A uniform electric field is produced between two vertical metal plates. We have a voltage, we have a separation. Draw lines to represent the electric field between the plates. So electric field goes from plus to minus. Here we have a plus, so that's going to connect to here. So our electric field is going to do this. They should be uniformly spaced and straight lines going from plus to minus. Calculate the electric field between the plates. E equals V over D. We have a voltage, a potential difference, we have a separation. This needs to be converted into meters because that's our standard units, and there we will go. Calculate the work done by the electric field on the alpha particle as it moves from AB to CD. Okay? Now, there are a couple of ways that you could do this. Either you can say, well, we have a constant force, so work done is equal to force times the distance traveled. So you can work out the force on the alpha particle and then multiply that by the distance. Or alternatively, you can say, well, we've moved through a potential of 450 volts and our change in potential energy, our change in energy is equal to our change in potential times our charge for an electric field. Either of those will work. You will get your charge of your alpha particle. An alpha particle is 2 protons and 2 neutrons, so that has a charge of plus 2e. And from the front of your book, E is 1.6 times 10 to the minus 19 coulombs. So there you have your charge. Multiplying it by 2, obviously. A beta particle moves from AB to CD. Calculate the ratio of the work done. So, our work done is proportional to our charge. Now, so our work done is proportional to our charge, right? We've just said that. If our work is proportional to our charge, a beta particle has a charge of minus E. It's got half the charge, you're going to do half the work, and so our ratio is going to be 2 to 1. Technically, it's going to be minus 2 to 1, but the amount of work done should be, so the ratio should be 2, I believe. However, I don't know if they want minus 2. If they want minus 2, it's because in one case you're doing work, and in one case you're gaining work into the field. But I think that's probably beyond this. So I think all they're looking for is a ratio of 2, saying that work is proportional to charge. And that brings us to the end of the paper. So I think overall a fairly reasonable paper. Hopefully this was helpful to you. If there was anything else that you wanted talked about that was question specific, please leave some feedback as ever. And I will see you in another paper. Goodbye.